Today is to continue with our discussion of the Koch determinant and some of its implications. But in thinking through what I was going to tell you about today, I realized that there was one slightly more elementary thing that I had not told you about that we will need in our discussion today. So I'll start with the first 10 or 15 minutes reminding you of this more elementary thing. And this more elementary thing has to do with what we can say about correlation functions. What we can say about correlation functions from the fact that we have conformal invariance. Okay. Now I'm going to derive what I need in a slightly more fancy way than is necessary, so that the generalization of this method is immediately applicable to what we're going to use it for, hopefully today. So let's start follows. Suppose we've got a sphere, and we've got points W1, W2, W3 up to Wn, and there's insertions at these points, O1 of W1, O2 of W2, and so on, On and Wn. Okay? This is an S2. Okay. What we certainly need, let's stick to S2. Some of what I say generalizes to other manifolds, but let's stick to S2. Okay. Now what I'm going to do is the following. I'm going to remind ourselves that T of Z had this expansion, sum over n ln over z to the pi n plus 2. Okay, whose inversion was ln was equal to 1 by 2 pi I dz divided by into z to the pi n plus 1 T of z. Right? This was the inversion if we expanded T around the origin. If we expanded around some other point, z will go to z minus that point. Okay. Now, let us suppose that I want to act ln on O1. Suppose I want to act the operator ln on O1. What that means is I take this little loop and surround it around O1. Okay? Now, of course, I could do that action. I could do that action by then doing the OP of T with O1 and then see what we can get. We could try that. But there is another way to evaluate the same thing when our correlation function is on the sphere. And that other way is to take this loop and distort it around so that it goes and surrounds the other points. Can you imagine that? We've got this loop on this point. Let's say there was this other point, there was just one other point. I take this, the sphere is like a globe. I take this contour and enclose the other point instead.
It means you are counterclockwise.
Exactly. So if my contour was counterclockwise around O1, it will turn counterclockwise around O2. In fact, it will turn clockwise around all the other insertion points. Okay? Now in many applications in the first few applications we use today, we will choose O1 to be identity. Which means we just put a little loop around any point where nothing is there, and then take it around and enclose all the other points. But in some other applications, we will actually use O1 not equals identity, so we'll just keep this general. Okay? So, what I wanted to, so what we just said in words is the following equation. Ln on O1, omega 1, O2 omega 2, On omega n. This correlation function is the same as equals, there's a minus sign because the clockwise. There is 1 over 2 pi I because of this 1 over 2 pi I. Then there is this factor of, then I'm going to do this m minus 1 times. So let's say q is equal to 2 to m minus 1 to m. Okay? because we'll have a factor enclosing each of the remaining operators. And then we have, now I'm doing it in bad notation, I'll just pretend I'm doing it on O2. And then the remaining guy is, 2 will be replaced by 3 and so on. Okay, I should write OK and so on. I won't do all that. Okay, then we have what? We have O1 of omega 1. Okay, and then we have T of Z O2. Okay, then the factor here was Z to the pi n plus 1, but that really should now be Z minus omega 1 to the pi n plus 1, because this was acting on the point omega 1 at the operator surrounding omega 1. Clear? Okay. O2 is omega 2 and then Om omega m. And then this is done for each of the points. Okay, so I could write here omega k, and you understand, right? Is this formula clear? This semi-formula clear? Okay, no confusion, right? Otherwise I'll write it out more clearly.
Does this look something like what?
Yeah. It's an implication of symmetry, so in some sense it's, we're not looking at the word identity, the way I use the word, is correction to conservation of current. So it doesn't look exactly like that from the way I use that word, but of course these are all related things because they're all implications of conserved, symmetries. So you can take that word identity equation and then integrate it and get something like this. Yeah. Okay.
So I was thinking that suppose I have 3 operators in circuit.
Yes. Yes.
And I was doing it over one point.
Yes.
Around one point. When I was doing it, going it around.
Yes.
Inverting it. So this loop will wind around the 2 operators, not just one operator at a single.
Yes, but now it's winding around 2.
Yes.
Now you shrink it to this.
Okay.
Okay, that you can do. So winding around 2 is the same as 2 windings around 1 each. There's no problem with changing the contour. Excellent question. Clear to everyone? Okay, other questions or comments as we proceed. Now, since this loop was circling around this guy, so this was a contour that is circling around O2. Okay, and then there's a similar one for circling around O3 and O4 up to OM. That's clear, right? Since this guy is circling around O2, this T and O are the nearest 2 operators in the problem. You can surround them by a disk where no other operators are inserted, because you can take this contour to be very close to O2. Okay, so we are justified in using the OP expansion for T with O2. Okay, but the OP expansion allows us to replace this guy with H2 O2 of omega 2 by Z minus omega 2 whole thing square plus del O2 omega 2 by Z minus omega 2 plus higher orders, but we're only going to pull out a pole, so anything that's not singular as Z goes to omega 2 will not contribute, so the higher order doesn't contribute. Okay, and now we've got a Cauchy integral. All the dependencies on Z are explicit. So we just want to pull out the pole. Okay? This guy is already pole-like. We have this extra factor of Z minus omega 1 multiplying all of this. So it's there ready to be Taylor expanded around Z equals omega 2. But we don't need it because this guy was already a pole. Any higher order in the Taylor expansion will make it regular. Okay, so this guy just contributes del O2 omega 2 over Z1 minus Z2. Because we're taking the pole, Z, this just contributes. This with here, this guy set equal to omega 2. Omega 2 minus omega 1 to the pi n plus 1. Because we're taking the pole, has that residue. Is this clear? Okay, it's a bit confusing, I know. Stop me if anything's too confusing. Okay? People are looking a little puzzled, I notice. You want me to say this more clearly, you should tell me. Okay, I'm going to continue, and then any point that you feel you want clarification on, we go on. What about this guy on the other hand? Once again, we need only a pole. So we have to Taylor expand this to first order. So we will pick up from here n plus 1. Then we will have z minus omega 1 to the power n. Okay? But at that point, we pick up the residues. We set z equals omega 2. So omega 2 minus omega 1 to the power n. And then H2 O2 of omega 2. Okay? And therefore, and then all the factors come out. And so this whole operation, the 2 pi I cancels because in Cauchy's theorem we get a 2 pi I. Okay, minus sign remains. So we have L n O1 O2 to OM is equal to, I'm writing the first term and then there are m minus 1 such terms, minus of n plus 1 omega 2 minus omega 1 to the power n H2 plus omega 2 minus omega 1 to the power n plus 1 del 2. Del 2 is the del operator acting on the coordinate 2. Okay? This whole thing acting on O1 to ON.
When you say ln O1, ln is acting on.
What?
In the left hand side,
ln ON is whatever you get by acting ln on O1.
that is just
Commutator of ln with O1. That's correct. It's this operation, the T operation surrounding O1. Okay. As I said, we will often choose O1 to be identity. So that quantity will just be 0, often. Is this clear? And then, of course, there are the other guys. Okay? So now let me write a proper equation. We get ln O1 O2 to OM is equal to minus sum over I equals 2 to m minus n plus 1, so I've got the minus, so n plus 1 omega I minus omega 1 to the power n hi plus omega I minus omega 1 to the power n plus 1 del I acting on O1 to ON. Is this clear? What's nice about this expression here is that it's a differential operator.
In that correlation function, OI will not be present.
In which correlation function?
Like after the bracket.
No, everything is present. Because you see, we had this loop surrounding O1, then we took it around. O1 is still there, it's not gone away. Okay? And when we act the loop on O2, we get either O2 or derivative of O2. So O2 is still there. Is this clear? Was something confusing here? This is actually a fundamental equation in conformal field theory. One we will use again and again and again for various purposes.
This is valid for primaries.
This is valid when all the operators inserted are primaries, because we've used the operator product expansion, assuming it's a primary. Correct. Only for primaries. Yes?
In that summation, we are doing integral of P of Z with every operator.
Now, finally, in the summation, there are no integrals left anymore. In this final equation, left-hand side was a correlation function of some operator. What operator? The operator you get by acting ln on O1, O2 and so on. Just a correlation function of these operators. Okay? Right hand side, once again there's no integral. It's just a sum of m minus 1 differential operators acting on the correlation function of O1, O2 up to On. Is this clear? What's really nice about this equation is that the right hand side is extremely explicit. Left hand side is a bit fuzzy, right? What is this Ln of O1?
That is not local. Ln is not local.
Well, n is low. I mean, we will get something. We can use OPE to get whatever it is. No, it is local. But that's not, the point is it's not explicit. See, suppose I give you a correlation function of O1 to On. What I mean by the right hand side is not some fancy conformal field theory stuff. It's just differential equations. It's just acting derivatives and multiplying the correlation function. Right hand side is explicit in the term in sense of functions. I give you the correlation function as a function. You know what to do to the right hand side. Okay? For the left hand side, how to make Lm of O1 out of correlation function of O1 may not be so clear to one. Right hand side is totally explicit. Okay? Now, for this, when this equation is most useful when we can also make the left hand side explicit, often to make it 0. Okay? Please.
When we took the contour around the other point,
Yes.
why did the T of 0 shift through that sequence?
Why did what shift? The T?
The T of z.
T of z. Okay. Let's just imagine it.
Can you draw how
Can I draw? I wish I had a globe. But okay, I will try. Okay. So I've got this, and if we have one more color, maybe not. Okay. I've got one operator here and another operator here. Okay. So we had this contour with T on it. Now T is an analytic function. As long as we don't pass T through any point of singularity, any other insertion, we can deform this contour. The contour with this T. Okay? So now we take this contour here and we make it bigger, 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 and make it until it surrounds this point. Just the other way. Sorry, maybe I didn't understand your question.
So I don't understand whether T convolutes with O1 O2.
No, you see, this is a correlation function. Imagine doing this inside a correlation function. Inside this correlation function, this is just some number. And we're taking it around here. All we're using is analyticity properties of functions. This is true for every correlation function, which is just some number, right? So we don't have to think of anything fancy. We've got a function of z, omega 1 to omega n. And on that function, this is true.
Yes.
That's all we've used.
No, I mean, we use the OP, right? OP was because
Correct.
of T and
Yes, correct.
so the ordering matters there.
What ordering?
So in order to use the T, O2, OP, T had to be next to
Well, firstly, we're in Euclidean space. Okay? So all operator orderings are the same. Maybe you're asking why. There are two things you might be asking. Okay? Let's get them, separate them. The first thing is this. When we look at action of operators on a Hilbert space, the ordering definitely matters. Okay? We're looking at just manipulations within the path integral in Euclidean space. Okay? In Euclidean space, there is no ordering issue. Just within this Euclidean path integral, there's no ordering issue. Okay? That is one question that you might be asking that is not relevant. Okay? The second question you might be asking is the following. We are allowed to use the OP only when we can find a little disk such that that disk includes the two operators we want to expand and nothing else. That is clear we can do because we can take this thing around. Okay, so I shouldn't have said functions. Maybe it would be clearer if I said we're performing this expansion always within a Euclidean path integral. Okay? Within Euclidean path integral, there's no issue about where you order. It's a path integral. Okay.
But there is an issue of this radial.
If you want to translate what you get from this Euclidean path integral into results about some Hamiltonian business for a particular quantization, it's true you can use the Euclidean path integral to deduce statements about operator, this is first and second, this is second and first. But right now all we're doing is manipulations within the Euclidean path integral. Just never think of these as within the Euclidean. If you remember our derivation of the operator product expansion, it was a statement just about Euclidean path integrals. The Euclidean path integral with this operator here and another operator there, take that whole path integral, and then you can, that's a functional of the boundary values, and you can shrink it to a point. Okay? In all of that, we never had to say Hilbert space. Okay, it's true we use the fact that there exists a Hilbert space to argue this was a convergent integral. Okay? But the manipulation was entirely within path integrals. Think of it that way. It's the least confusing. Is this clear?
So when we are applying ln on O1,
yes.
that my Tz was in O1 in the counter.
Yes. Yes.
But when I am doing Tz O2 and taking the counter, so that Tz and O2 will be.
I'm shrinking the contour around that.
So Tz and O2 will be
The nearest ones.
And for the summation, I am doing same.
For all of them. Okay? If I had two of them, so this way, this guy would be this way, and this guy would go like this way, and like this way. So this can be deformed to this plus this.
Tz is going in every contour.
Tz is on the contour, yes. Okay, that's an integral. So Tz is here, plus here, plus here, plus here, plus here, plus here.
A slight,
Gone.
slight digression to what you
Gone.
what if there are lines connecting
What do you mean lines?
Wilson lines?
What do you mean Wilson lines? Are you thinking of a gauge theory?
Yes.
Okay.
Like it will not just become two circles, right? There will be some.
But we have to say what we're saying. You're saying, suppose we have not local operator insertions, but some line defect. Maybe that's what I'm hearing from you. Okay, then you will not be able to go through that line defect. But that is, let us forget about that. We're not looking at that, right? We're just looking at local operator insertions. I mean, it's an interesting question, and we can come to that. But for this purpose of this correlation function, in the absence of line defects, we don't need to worry about it. Okay, I'm sorry this presentation was unclear, but please keep going. Is there anything confusing? Any residual, even slight doubt you have? Say it, because I'm sure your neighbors also have that. Or wouldn't have, that doubt hasn't occurred to somebody else, but it's useful, right?
The calculation wise everything is fine, but what it physically means that I have to operate somewhere on the sphere and I X over this to the ring.
Yeah.
It's constrained by the data given by all other operators on the sphere.
Yeah. Yeah. It's sort of like this, right? That what I'm saying is not exactly accurate. But had you had a symmetry that annihilates the vacuum, actually that is accurate here only in the case of L0, L1, and L minus 1. But just to get the sense of the derivation, had you had a symmetry that annihilates the vacuum, you can act with that symmetry generator on the right vacuum, and then take it through to act with the left vacuum. So the action of the symmetry on one is related to the sum of the actions on all the others. Did you understand what I mean? I'm not going to emphasize this because what I said here for exactly what I'm doing is not exactly accurate. Because T does not annihilate the vacuum. Okay, so but it's the same sense. We're doing that kind of thing, but accurately. Okay, other questions or comments? This manipulation, as I said, we will use many times through this kind of manipulation, also this equation. We'll use many times in our study of conformal field theory. So it's good to get it totally straight. Okay, great. Everyone's now happy. Everyone's now happy. So now we will use this. We will use this. I hope I've got all the Factors right. I'll keep this on the board so we can see it, and then let's try to use it. Okay, let's start by working out what this L operator is for the cases that we will most need. Let me do it here. Okay, let me clear this and do it here. First, let's do L minus 1. It's the easiest of the lot. You see, if n is equal to minus 1, then this guy is 0. Okay? And this guy is to the power 0. So L minus 1, when we have L minus 1 O1 to OM, this is simply equal to sum over I equals 2 to M minus del I on O1 to OM. Okay? Clear? Now let us immediately derive a consequence from this. Let's choose the condition, let's choose O1 to be the identity operator. By that I mean the following. By that I mean, suppose we had we had only m minus 1 insertions, and I just chose for fun to put a little contour around a point where there's nothing, and then deform it around the rest of the operators. This guy was obviously 0 because I could shrink it to nothing. Okay? So I get 0 is equal to, and then whatever else I get. Okay? So if I chose that case, so that O1 was equal to identity, I should have really, if I'd been, should have put it on M. So anyway, what I get is 0 is equal to sum over I is equal to 2 to M del I on, now O1 I can omit because it was identity. O2 to OM. This is not O, it's 0. Is this clear? And what does this tell you? This is the statement of translation element. It's the statement that if I translate the location of every operator insertion by the same amount, the correlation function doesn't change. This is a differential version of that. Okay, so of course this is something we knew, derived in a very sophisticated way. Clear? Okay. Let's now do the same thing for L0. Let's do L0. For L0, what does our operator become? Okay, so L0, n is equal to 0. So we get this L0, the operator becomes omega I minus omega 1 to the power 1 times hi plus omega I minus omega 1 to the power 1 to the power 1. Okay, omega I plus omega I to the power 1 and del I. What? N is 0, so? Thank you. Okay. Okay, once again we'll choose O1 to be identity. Okay, once again we choose O1 to be identity, and so we get the equation that sum over I hi plus omega I minus omega 1. Omega 1 now is not any point because we've inserted identity there, so it could be just anywhere. Right? Because we could insert identity anywhere. Del I on O2 On I is equal to 2 to M is equal to 0. Now what is this equation? You see, as we know, except for the point at infinity, the sphere is the same as the plane. Okay? Given a sphere, there's no distinguished point. You can choose any point and say, this is going to be the origin of the plane. And the antipodal point will become infinity. So let's choose our origin of the plane to be at omega I. You can always do that. Okay? And then this becomes the equation hi plus z del by del z, sum over everything, is equal to 0. It's the equation that tells you that the net dimension of correlation functions, the net power of 1 by z of the correlation functions, is the sum of the dimensions in the operators. Okay, so if you've got a correlation function of operators with dimensions h1, h2 up to hm, or h2, h3 up to hm, the net homogeneity of a correlator in omega 2 up to omega m must be 1 over omega to the power sum over h. That's what this is telling you. Right? It's just a statement about homogeneous functions. Is this clear? No. Okay. So let me say this again. Let me now go to this particular coordinate where we go to the plane. Omega 1 is equal to the origin. Now this equation becomes what? It becomes sum I is equal to 2 to m hi plus zi del by del zi on omega 2 O2 to m equals 0. This is clear? And then there is this lovely theorem about homogeneous functions, right? The homogeneous function of degree n, when you act with zi del by del zi on that, gives you m, let's say degree q, gives you q times that function. So how is this going to vanish? It's going to vanish if this object is a homogeneous function of degree minus sum over hi's. Okay, so correlation functions have to be homogeneous functions in their coordinates of degree minus sum over hi's. Again, this is something that's obvious, right? We've used it many times before. We've used it when discussing the OP and so on. It's not something new. But it's nice to see it come out of this, where you don't have to put, you're not suspicious about what assumptions you're using or what words you're saying. It's just coming out of formulas. Clear? Okay.
One more thing. Let's say we have just two operators in this, O2 and 2.
Yeah, lovely.
And we know that this is non-zero only if the lemma, the scaling lemma of O2 and O3 are equal.
Okay, but how do you know that? We're going to derive that now. That comes from L1. Excellent. Excellent. So, okay, let's move towards that. Okay? Let us now do what Shreyansh, right? Shivansh, sorry, I'm sorry. Let us now do what Shivansh wants. He wants us to study the simplest correlation function in the world, namely 2-point functions. Okay? So let's take O2. Let's move to the plane. Let's move to these coordinates. Okay? And let's take O2 of Z2, O3 of Z3. Okay? First thing, the first equation has told us is that this guy is a function only of Z2 minus Z3. Because sum over del I on it is equal to 0. Okay? Translation invariance. Second thing, let's say that this guy had dimension h2 and this guy had dimension h3. The second thing from this homogeneity tells us that the function must be of the form z2 minus z3 to the power h2 plus h3. Okay? So far we've concluded that O2, O3 has to take this form times some number. So far nothing has told us that this 2-point function had to have same h's. However, you know that this 2-point function, when you slice, is going to be an inner product between two states. You know, inner products between states with different energies vanish. So that better be that what you said was correct, that this 2-point function is only clicks when h2 is equal to h3. How do we see that from this language? Well, we see that from this language by acting not with L1 but with L minus 1 but with L1. So now let's work out the operator L1. Okay, so L1 here gives us a factor of 2, and then omega I minus omega 1, the whole thing to the power 1, hi, plus omega I minus omega 1, the whole thing to the power 2, and del I. Right? Now let's go to our plane coordinates. So omega 1 is 0, omega I is zi. So our differential operator becomes, the differential operator becomes 2 zi hi plus zi squared del I. If I act with this on each of the two operators, the sum of these two should give me 0. Is that conclusion clear? That if I act with this plus the guy on 2 plus the guy on 3, I should get 0 on the correlation function. Okay, but we already know that the correlation function takes, okay, so let's write this down really explicitly. So this is 2 z2 h2 plus z2 squared del 2 plus 2 z3 h3 plus z3 squared del 3 on, we already know that it takes this form, some number times z2 minus z3 the whole to the power h2 plus h3. This has to be equal to 0. Okay, now let's just work it out. It's a pain, and often we will not work out these things. I will just tell you when you do this, when we have more complicated algebra, but in this case, let's work it out. Okay. Of course, these are just multiplications, so we get 2 h2z2 plus h3z3 from here, right, multiplying this guy. Now what about this guy? This by divided by, okay, so everything by this number times this number, and let's say everything divided by z2 minus z3 to the power h2 plus h3. Okay. Now what about this differential operator? This guy gives us plus, let's say, okay, let's multiply, let's do z2 minus z3 to the power h2 plus h3 plus 1. So this has an extra z2 minus z3, because when we differentiate we'll get an additional power there. Okay, let's do this guy. So this is plus z2 squared, and then when we differentiated we got this fellow, but to the power h2 plus h3 and with a minus sign. Good. And then we get plus z3 squared. And the only difference is when you differentiate here, you pick up an extra minus sign. Okay, times h2 plus h3. Clear? Okay. So this thing is number by z2 minus z3 to the power h2 plus h3 plus 1. And now this guy is z3 squared minus z2 squared. So it's z3 plus z2 into z3 minus z2. Okay, so we get an extra factor of z2 minus z3 into 2h2z2 plus h3z3. Okay, and here we get minus z2 plus z3 h2 plus h3. Please correct me if I've made a mistake. Okay, looks good. Now this has to be equal to 0 for all z2 and z3. How can that work? one of the factors has to vanish. Either this number is 0, in which case the correlation function is 0. This factor is not 0 in general. So the other way it could work is if this factor was identically 0. But this factor is not identically 0. Okay? It's a linear thing, right? So we can write it out. This factor is, the coefficient of Z2 is 2H2 minus H3 plus H2. So that's H2 minus H3. Plus Z3, this was again a factor of 2, right? The 2 multiplied everything. Z3 into H3 minus H2. So it's not identically 0 unless H3 is equal to H2. So we have two options. Either H3 is equal to H2 or the correlation function vanishes. Okay? So scale invariance and translation invariance didn't give you the condition you wanted. Okay? Scale invariance and translation invariance didn't give you the condition you wanted. But if you also include invariance under the special conformal transformation, L1, you get what you wanted. Is this clear? So 2-point functions only click between operators with the same scaling dimension, and their form is completely determined by conformal invariance. Okay? Now one can do the same exercise for 3-point functions. One can do the same exercise for 3-point functions. Okay. The first condition is that it's function only of difference between coordinates. That, of course, is clear. So clearly, and the second condition is that of homogeneity. So clearly the answer must take the form Z1 minus Z2 to the power A1, let's say A12, Z2 minus Z3 to the power A23, and Z3 minus Z1 to the power A31 times some number, of course. Clear? What we can say from homogeneity is that A12 plus A23 plus A31 must be equal to H1 plus H2 plus H3. That's the L0 constraint. Okay, but at the moment that's all we can say. But now we act on it with L minus 1. Okay, an exercise that's similar to the one that we undertook but more painful to do algebraically, and one that I will not try to do here. Okay, when you undertake it, it's an easy exercise, right? You act on this form by the sum over L's, and you impose the condition that you get 0, just, okay? And you will find the following. You will find that the only way you get something non-zero is if A12 is equal to H1 plus H2 minus H3 by 2. A23 is equal to H2 plus H3 minus H1 by 2. And A31 is equal to H3 plus H1 minus H2 by 2. Then I've got the by 2's wrong, sorry. Yeah, sorry, not by 2. Thank you. H1 missing. Yeah, now it satisfies. Right, because each H1 appears 2 times. Yeah, sorry. I got it.
So by determining that constraint number?
The constraint number you cannot determine by these kind of arguments. Firstly, for 2-point functions, the constraint number is ambiguous because you take you've not particularly said whether you're dealing with O or 5 times O. O is a primary source 5 times O. You can scale your operator, but you can get any number you want. Because it has to have a particular sign by unitarity. You can't change the sign because you can change the operator by square of it. But okay. Now what you can ask is, given Suppose I take my operators and make the 2-point function so that that constraint number, that hash number for 2-point functions is 1. Now what number you get for 3-point functions is meaningful. Okay, or you could say it in terms of the number you get by 3-point function divided by the square roots of the numbers you get for 2-point functions. That is scale invariant, that you cannot change by rescaling your operators. Okay? That quantity is called a structure, these are the CIJKs of conformal field theory, is the basic primitive data, apart from the operator spectrum, these 3 numbers plus 1 or 2 other things, okay, modular invariance, including 1-point functions, completely determine a conformal field theory. Okay? And that is like dynamical data, the CIJKs. To determine them requires real work. We will do some of that real work for minimal models. Okay? But it's not going to follow so trivially. Is this clear? Okay? Fine.
To go from this sphere to plane, we have to do a conformal transformation.
To go from sphere to plane, we had to do a conformal.
And the equation we derive is
conformal. Yeah, go on. Please go on.
and the equation we derive for this differential equation, the
Yes.
right-hand side.
Yes.
I'm just worried that while doing this conformal transformation, we might pick up some factors, coordinate transformation. In the case of L1, it doesn't, because
Okay. You want, okay. You see, we could do this whole derivation on the plane, provided we are allowed to shrink the contours at infinity. Okay? And that we can always do as long as there are no insertions there. Okay? Because for that one little thing, we can do the conformal transformation, but it was empty. So there was no conformal transformation. So you just shrink it. So while I presented this argument to you first on the sphere, we could have just done the argument always on the plane. Okay? That would be one way of seeing that your worry does not apply. In fact, when we actually do practical calculations, that's almost always what we'll do. It's a pain to work on a sphere, right? Because, yeah. Whereas here, this is very clear.
This should also work for any other manifold, right?
It works as long as there's no obstruction to taking things around. Yeah. So, if you choose the right kind of contours, it will work.
Manifolds with no boundaries.
Manifolds with no boundaries, and you want to make sure that you're doing, for the right insertions at the beginning, I think it will work. There will be things you can say and things that will be manifold dependent. Yeah. But let's stick now to this. Yeah. So it's by far the simplest case. And sufficient for most purposes. Because sphere and torus completely determine the conformal field. Okay, excellent. But both excellent questions. Any more questions or comments? Okay. Now, suppose we did the same exercise for 4-point functions. Okay? Suppose we did the same exercise for 4-point functions. We're doing so well, right? 2-point functions form is completely determined. 3-point functions form is completely determined. You might think, well, maybe 4-point function form will be completely determined. Okay? And that would have been sort of really powerful. Turns out not to be the case. Okay? Again, you can try this little exercise. You can try to do this little exercise. And you can try to do this little exercise. And you will find the following. Okay. You will find that if you have O2, I'm calling it O1, okay? O1, O2, O3, O4. Okay? I'm calling it O1, O2, O3, O4. Okay? You will find that if you have Now, I only remember the numbers. There's an extension for every case, but let me take the case where there's this one, both these have dimension h1 and both these have dimension h4, let's say. I would have to remember and give you the same answer for the general case. Maybe one of you knows it. Okay, but any correlation function of this form, omega 1 minus omega 2 to the power 2h1, omega 3 minus omega 4 to the power 2h4, times a function of what is called cross ratios. Okay, z1, 2, z3, 4 by z1, 3, z2, 4, where z1, 2 means z1 minus z2. Okay? Any function, sorry, I'm writing omega here and z, let's call it z. Any function that's of this form obeys all these quote-unquote word identities, these constraints that you get from L0, L1, and L minus 1. Okay, I've given you the answer. First, you see, this guy has the form of a 2-point function times a 2-point function. Okay, so immediately you sort of see that the constraints you're going to get will work out, because they work out 2-point function by 2, piece by piece. What's non-trivial is that this does not, what's in some sense disappointing, is that this does not completely determine the form. Okay? You can have an arbitrary, undetermined analytic function. Okay? An arbitrary, undetermined analytic function multiplying this otherwise determined thing. Okay? Though I've given you the answer only for the special case where h1 is equal to h2 and h3 is equal to h4, there is a generalization with some mixing up, which I'll tell you about next time. I haven't brought it with me.
This can be expected because you have 3 equations and you have 4 variables, right?
This can be expected because we have 3 equations and 4 variables. Yeah, I think you're right. Because we have 3 equations, because of the L1, L0, L1, and L minus 1. Yeah, 3 differential equations and 4 variables. Exactly, I think that's right.
Also, what will happen if you change 2 and 3 in that formula?
In which formula? This one?
Yes. Let's say 2 and 3.
Yeah, so I gave you the formula when H1 was, these two had the same H, and these two had the same H. Okay? However, that's not a good answer. My generalization will also pick out pairs, the generalization I'm not giving you. What if you can also write it with this and this and that, and those will differ by a particular choice of function of cross ratios. Sorry to have this discussion so abstractly because I don't remember that form. But do you understand what I'm saying? I'm saying you take the ratio of those 2 prefactors and it's a function of cross ratios. Okay, so this is the same thing because we haven't said which function of cross ratio.
So, are you saying that if H1, H2, is, all these are distinct lengths?
Distinct.
It will be 0.
No. What will be 0?
If H1, H2,
What will be 0?
that correlation.
No, I'm not saying it's 0. I'm saying I don't remember the answer. It's probably in this book. If you want, since this has come up, so let me. I'll probably get it out of. I'll get it out of the book. One second. Fortunately, I don't know this book very well, so I don't know where to look. Correlation functions. Give me 1 minute, otherwise I'll tell you. We'll have the discussion more clearly once I give you the answer, once I write down the formula. Here, good. The generalization of this is that you have define H is equal to H1 plus H2 plus H3 plus H4. Okay, and one way of writing this, there are many ways, but one way of writing this prefactor is 1 over product I less than j Zij to the power h by 3 minus hi minus hj. Is this clear? Let's check that this meets all our requirements. Okay. Let's I less than j. So there are 6 of these guys. Okay. So when we add this up, when we add up all these powers, we will get 2h let's see. Yeah, we will get 2h, sorry, not 1 by, this was in the numerator. This was the factor. Let me check that it's working, then we'll discuss it. How many of these factors were there? There were 6. In how many factors does h1 appear? In 3 of them. So we will get 2h minus 3h. So it will be 1 over minus h. So, okay. So claim that there is a way of writing this general factor, which is this. So the most general correlation function is O1, O2, O3, O4 is equal to product I less than j, Zij to the power h by 3 minus hi minus hj. This is always true, no restrictions on dimensions, times some function of these cross ratios. Okay, this is the most general case. Now, I told you something else there. If you evaluate this for my special case, it will not in general work out to what I said, but the ratio of this by that will turn out to be a cross ratio. Okay? So, if this f may not be that f, but related by some factor. Is this clear, or if it's not clear, I'll work it out. Is it clear? Right? Is it clear? Okay? So, because we have prefactor times function of cross ratio, the prefactor is ambiguous. I give you one prefactor, you multiply by any function of the cross ratio, that's an as good prefactor. So the question of what that prefactor is not a clear question. You can make various choices because we're multiplying it by an undetermined function of cross ratios. There are many different ways to say this answer. Is this clear? Okay? This is one nice symmetrical looking answer. Nice symmetrical looking way. Okay? Great. So when we were studying 4-point functions, the important thing is that there is an undetermined function. Okay? There is an undetermined function of cross ratios. Okay, there's an undetermined function of cross ratios that needs to be determined in order to find the thing. Okay, please.
The other ln constraints.
Other ln constraints. Now, these other ln constraints are not as simple as this, and the reason for this is related to Shivanshu's question, which is, if we're working on the plane, you want to be able to take these other ln's and have them annihilate the vacuum. And this will not always happen. vacuum at infinity. Okay? So maybe I can try to explain that. So these constraints, physically, let me say what I'm saying first. Physically, the vacuum of conformal field theory is annihilated by L0, L1, and L minus 1. Okay? But it's not annihilated in general. It's not annihilated both from the left and from the right. Okay? By the other L's. Okay? So, the vacuum at infinity, what you can think of is 0 being the Ket vacuum and infinity being the Bra vacuum. Okay? This contour going and closing off and giving you nothing at either 0 or infinity is the statement that these L's annihilate the vacuum, the Ket vacuum and the Bra vacuum. And both these statements will not be true for L's other than 1 minus 1 and 0. Okay? So for this reason, for this reason, the constraints that we get from L0, L1, and L minus 1 are very simple ones. Okay? Whereas it's not so clear what you get from the other L's, because you get something undetermined when that guy hits the vacuum. Okay? Is this clear, or would you like more detail? Yes?
But if you have positive L's,
yes.
then left hand side is still 0, right?
But it has to annihilate both vacuums. Because it has to be 0 when you do this, and 0 when you take it round. Let me explain this in more detail.
The left hand side is just doing this. Then you do whatever you do on the other.
Okay, but you have to be able to take it round infinity. Say we're working on the plane. You take this thing, and you have to take it round infinity. So you have to start with something that's 0, and end with something that's 0. Both need to be true. Okay? Now, let's look at the formulas. Ln, okay, was z to the power, say we put our initial insertion at 0. We wanted to do it for identity. We wanted the statement that L annihilate identity, which is L annihilate the vacuum. Let's check when it's true. Okay, so we wanted z to the power n plus 1 t of z 1 by 2 pi I. Okay, this should be 0. But this is only 0 for n equals minus 1 or larger. Right? So, the statement that Ln was nothing, that annihilated the identity, was true for n greater than or equal to minus 1. Good. Now, we need the converse statement, that it annihilate the identity at infinity. Okay? So we have to do that. We have to check how it annihilates infinity. For that, we need to do the conformal transformation. Z goes to 1 by W. Okay? That conformal transformation gives you an extra weight, because this T operator has, it's not quite primary, but ignoring that subtlety, because this T operator has this extra weight too, we will get some extra factor. But because Z is going to 1 by W, the inequality will go the other way around. Instead of being greater than or equal to minus 1, it will have to be less than or equal to something. And that works out to 1. Is this clear? Okay? So this condition, this condition that we're working on the plane, is this nice simple thing only when the operators are L1, L0 and L minus 1. Okay? What the relation, we can see the physically what's happening is this. Because LNs don't annihilate either the bra or the Ket vacuum. If you take L, act on the Ket vacuum, and take it through all the operators and hit the bra, Okay? You're not getting a condition just on that correlation function. You're getting a condition that tells you that the correlation function is related to another correlator with a new insertion. The new insertion is whatever you get by acting on either the ket or the bra with these L's. Okay? Another way of saying it is that while these Virasoro generators, this whole Virasoro symmetry is a symmetry of the theory, that symmetry is spontaneously broken down to SL2R. Because what do we mean by spontaneous symmetry breaking? We mean that there's a symmetry of the Lagrangian, but it's not a symmetry of the vacuum. Those generators don't annihilate the vacuum. So another way of saying it is that in conformal field theories, the Virasoro symmetry is spontaneously broken down to SL2R. So the non-spontaneously broken symmetries give you simple word identities. But the spontaneously broken symmetries give you Goldstone theorems. They give you that you do something to the correlator and you get another correlator with one insertion of the Goldstone mode.
So even that box statement is true only for -1.
Yes. This statement was always true. It's whatever Ln does acting on. Oh, but you're saying to take it round. Yes. Yes, even that statement. Well, yeah. Even that statement would exactly. If these L's were negative, that will always work. If we have L, because all we want is that it annihilate the bra. Okay, so L less than equal to 1. This is actually true only for Ln n less than equal to 1, because I needed to take it around the bra. Yeah, okay, thank you. Yeah.